Welcome to Theory of Computation. This is lecture number 19. In the last lecture, we started our discussion on descriptive complexity. The basic scenario is that we have a string X and we want to describe this string in as few bits as possible. And what we are searching for is the definition of the shortest possible description of a string X. You can think of this scenario as two people who are sitting in two different rooms, and one of them wants to communicate the string X to the other person. What we want to know is how can we describe this string or compress this string or so that we can send this string from room 1 to room 2, and the other person will be able to unambiguously decode this string. Well, one way to do this is the two people agree on a compression algorithm. But we are following a completely different approach. Our approach is going to be that the first person is going to send an algorithm. So he's going to send a description of an algorithm across. And when the other person runs this algorithm, the algorithm will produce X. So this is, in some sense, the most flexible way of doing compression. Roughly, that's what we are going to call the description, the smallest description of a string X. We also looked at this paradox, which was called Berry's paradox. Berry's paradox arises when we look at the following English sentence: the smallest positive number that cannot be described by less than, say, 20 words. When we look at this sentence, we realize that this sentence itself is describing a number. If we count the words in this sentence, it turns out to be less than 20. Therefore, the sentence seems to be describing a number which requires more than 20 words in less than 20 words. And that is a paradoxical situation. The way we understood what was wrong in Berry's paradox was that the word description does not have a precise meaning in English. Once we have a precise, mathematically sound definition of the word description, then it would not be very easy to come up with a sentence like this. In fact, if we look at our definition, it's not clear at all that one can actually write down a sentence which again leads us to Berry's paradox. Berry's paradox is very interesting in this theory, as Gregory Chaitin has shown us that one can actually come up with a Berry-type paradox in this theory, and that leads to an alternative proof of Gödel's theorem. That is an extremely exciting way to reprove this great theorem that we have been studying. However, we would not be going that far in this theory. We will just be content with proving very simple theorems and just looking at the basics of what this theory tells us. This theory is trying to capture the notion of what information is, or how much information is contained in a particular string. The way we define information in this theory is the information in a string is the length of the shortest description of that particular string. Thus, if a string does not have a lot of information, then we should be able to describe it very succinctly. I gave you an example. For example, let us look at the digits of pi. I'm sure all of you must have studied pi when you were young, and you know a lot of basic facts about pi. The digits of pi do not show any pattern. We know that pi is an irrational number, so they never repeat. Furthermore, they don't seem to show any obvious pattern at all. So the digits of pi seem to be an infinite string which is more or less random looking. However, the digits of pi do not contain infinite amount of information. The reason for that is pi can be described very succinctly. There are very simple formulas, infinite series that equal to pi. A description of any one of these series in principle is describing all the digits of pi. Thus, the digits of pi is an infinite series which has finite descriptive complexity. Same is the case with any natural, transcendental, irrational number for which we have formulas for computing that number. If we can find a succinct formula for computing the digits of any number, then that number's digits have finite descriptive complexity. Now what we will do is we will start putting all these definitions into a mathematically precise formulation. So the overview of today's lecture is going to be as follows. We will start with the definition of information. Then we will talk about minimum length descriptions. Then we will define what is the descriptive complexity of a string. And in the end, we would talk about incompressible strings and prove a few interesting theorems about it. We have been asking extremely fundamental questions in this course. For example, in the first part of this course, we asked the question, what was an algorithm? And we came up with a formal, precise definition of an algorithm. Right now, what we're doing is we're asking the question, what is information? It often happens in mathematics that when you ask mathematicians to come up with a precise definition of a notion, that area starts blossoming because now we can formally talk about it. The definition of information is going to be given in this part of the course, and this is through what we call descriptive complexity. I must tell you that there is another way to describe information through entropy theory, and that is an extremely large field. We are not going to follow this route. We will just look at the definition of information the way it is given by descriptive complexity theory. Let's, as an example, look at the following two strings. As you can see, the string A, if you look at it, is an extremely simple string. It is just 10, 10, 10 repeated many times. On the other hand, the other string which is shown on the screen B is 10, 1, and then the pattern sort of breaks. You have 0, 0, 0, and then 1, 0, 1. So it does not seem to follow any fixed pattern. Intuitively, A seems to have less information than B. Why is this that A seems to have less information than B? Well, that's because I can describe A to anyone in a few words. What I can do is say that A is 10 repeated, say, 20 times. On the other hand, if I try to describe B to a friend, the string B to a friend, there doesn't seem to be a very simple way, a very short way of doing it. Since B does not have any pattern, what I will have to do is memorize the whole string B, and when I meet my friend, I will have to say the whole string B out to them. So in this sense, B has a lot of information and A has little information. If I want to memorize A, all I have to do is memorize its 10 and how many times it was repeated. On the other hand, if I have to memorize B, I have to memorize the whole string, and so there doesn't seem to be any way of compressing this string B. So we will say that B has a lot more information. If I want to communicate it across some channel, I'll have to communicate the whole string across that channel, and therefore there doesn't seem to be a way of reducing the information that is there in the string B. What we want to do is we want to make this notion very precise. There are two ways of describing the string A. One is to write its individual bits, and the other is to simply say that it is 10 repeated 15 times. We will be interested in the shortest description of a string. So, what is going to be the shortest description of a string? What we need to do is be very clear on the notion of what a description is. So what we want to do is we want to come up with the most general way of describing a string. How can we describe a string in the most general way. We do not want to commit ourselves to any particular compression algorithm or description algorithm. Well, the idea is going to be very simple. We will allow our descriptions to describe algorithms. What we want to do now, we want to impose two restrictions. First of all, we will always be talking about describing strings of zeros and ones. The second thing is that each description must also be a string of zeros and ones. So in some sense, we are trying to compress strings. As computer scientists, you know that any other alphabet can be converted into zeros and ones. Anything can be encoded as zeros and ones. So this is an extremely general way. What we are doing is we're talking about the minimum length description of 01 strings, but 01 strings can capture any other alphabet also. The most general way to describe a string S is to give an algorithm A that produces the string. Thus, instead of describing a string S, we simply describe the algorithm A. Let us make this idea much more precise. Well, what is an algorithm? We have a formal notion of what an algorithm is. An algorithm is simply a Turing machine. So, a description of an algorithm is going to be the description of a Turing machine. Formally, what we will do is we will consider a Turing machine M and a binary input W to M. Suppose we want to describe the pair M, W. How can we perform this encoding? Well, what we can do is we can take the description of the Turing machine M and follow it by W. And we can say that this way we have encoded the pair M, W. There is something slightly wrong with this way of describing pairs. Suppose you send such a description to a friend. So your friend knows that what you have sent them contains the Turing machine, the description of the Turing machine M followed by the string W. However, they will not be able to tell where does the description of M end and W begins. So, in order for you to describe a pair, you will have to be more clever. You'll have to somehow let your friend know where the description of the machine ends and where the string W starts. So let's give this another try. To avoid this problem, we have a convention now. All the strings in the description of M would be double. The description will be followed by a 01, which is in some sense a stopper, which informs that the description of M has now ended, and then we can simply write down concatenate W. With this rule, there will be no ambiguity in finding out where W starts. So, what you do is you take the description of your Turing machine M and you repeat every bit twice. So, if the description was 0101, instead you would send 0011 0011. After that, you would write a 01. And then you would write down the string W. Anyone who reads this description and knows this convention will be able to tell where the description of M ends, because 01 acts as a stopper, as a delimiter, which separates the description of the machine from the string W. So what we can do is now we can communicate a description of a machine followed by a string to our friends. Let us say we receive the following string, which is shown on your screen. As you can see, the first 01 that you encounter in this string has been bolded out. Before that, all the occurrences of zeros and ones are doubled. Therefore, in this case, we can tell that the description of the machine M is 100101101, and that is obtained by taking the first part of the string and undoubling it. The string following that is whatever comes after 0, 1, which is 1, 0, 1, 0, 1, 1. So this way, in these descriptions, we can unambiguously get the algorithm out, which is the description of this Turing machine, and the string that follows the algorithm out. This is the convention we will follow. So given any Turing machine M and a string W, what we can do is we can run M on W, and suppose this Turing machine outputs X. So suppose I have a Turing machine M, and when I run this Turing machine M on a string W, the output is X. Then what can I do? I can send M followed by W, the way I told you to encode it, to my friend, and if he knows the convention, he would be able to separate out the machine M from the string W, and then he will run M on W. The answer would be X, and he would say, my friend wanted to send me X. This is what we are going to call the description of X. So the description of X is a Turing machine M followed by some W, such that when you run M on W, the output is X. In order to describe the string X, we simply describe MW such that running M on W outputs X. Well, one question we can ask is, there can be several Turing machines which say produce X on the empty string. There can be several Turing machines which produce X on when you run them on 0, and so on and so forth. In fact, if you think a little bit about it, you would realize that X can be described in infinitely many ways this way. There are infinitely many different algorithms which will produce X. So which description would we choose? The idea is we will choose the shortest description. However, for a given string X, there may be many TM and input pairs that describe X. The minimal description of X will be denoted by D of X, and it is the shortest string M, W such that two properties hold. One is when we run M on W, it halts, and the second is running M on W outputs the string X. Well, now what if there are several shortest such strings? In this case, D of X is going to be the lexicographically first such string. So D of X is the shortest pair, shortest string M, W, such that when you run M on W, you get the output as X. The descriptive complexity of X, which we will write as K of X, is going to be the length of the shortest description of X. It is the smallest possible description of X. Well, what we're saying is that the shortest possible description of X is not given by describing X, but given by describing a procedure that produces X. So what I do is I take a procedure or a Turing machine, formally it is a Turing machine, and give you some data. I describe you a Turing machine and data, and you run that Turing machine on the data and the output is X, and that is going to be the description of X, and K of X is the minimum length of the minimum description of X. Let us look at a particular example, Java. This is a practical example. Let's say that you visit a web page. So you're visiting a web page, and on a remote computer, there's a Java program with some data on it. When you click there, the Java program is transferred to your computer. And then you run that Java program and it starts producing fascinating output. What happened in this case is the output that the program started producing, the fascinating thing that you were looking at, is X. That's what the other person who made the web page wanted communicated to you. However, they did not communicate what comes on your screen to you. What they communicated was simply a program that you could locally run and look at the beautiful things that are coming out on your screen. So X is what is on your screen, and the description of X is the Java program that you downloaded. So K of X is the smallest description of X. It is sometimes called the Kolmogorov complexity. It's also called Kolmogorov-Chaitin complexity, and that honors the two scientists who have really contributed a lot to this theory, and therefore sometimes it's named after them. So Kolmogorov complexity, if you ever hear the word, or Kolmogorov-Chaitin complexity, you should always think of what we are calling descriptive complexity, or what CIPSA chooses to call descriptive complexity. In fact, you have guessed it right. The K in K of X actually is once again chosen to honor Kolmogorov, who came up with these notions and proved a lot of theorems in this area. It is measuring, Kolmogorov complexity is measuring how much information is there in a given string. It also makes sense to talk about descriptive complexity of infinite strings, but we will not do so. As an example, I'll once again remind you that the digits of pi is an infinite string with finite descriptive complexity. As you can have Turing machines which, when you run on some input, start producing output and never halt. So we can say that these Turing machines describe infinite strings. However, if a finite program describes an infinite string, then we can say that the amount of information in that infinite string is finite, because I can have a finite program, and this, so for example, I can have a finite Java program which, when you run, just starts writing 10101001 forever. This program has fixed length, and I can write this Java program and put it on my web page. Anyone who downloads my program and runs it will see a sequence of 101010 which never ends. So in some sense, I have communicated the sequence 101010 which never ends using only a finite amount of information, that is, by just communicating the Java program across to the other user. Let us prove some simple but very useful and intuitive facts about descriptive complexity. The first fact that we are going to prove is that there is a constant such that the descriptive complexity of a string is always less than or equal to the length of the string plus this constant. Why is this interesting, important, or intuitive? Well, what we are trying to say is, if we want to describe a string X using our methodology, then our description will never be much larger than the length of a string itself. The second thing we are going to prove is that there is a constant C, and mind that it may be a different constant than the one that is given in part 1, that there is a constant C such that the descriptive complexity of XX is within an additive distance of the descriptive complexity of X. So what we are saying here is, if I want to describe you the string X followed by X, then I do not have to give you a much larger description than that of X itself. So what I can do is, the description of XX, the shortest description of XX, is going to be only a constant size larger than the shortest description of X. Let's look at the third property. There's a constant C such that the descriptive complexity of XY is less than or equal to twice the descriptive complexity of X plus the descriptive complexity of Y plus a constant. So what this is saying in some sense is that the total information in XY does not exceed the total information in X plus the total information in Y plus C. Actually, this particular result, the way I've stated it here, says that the total information in XY does not exceed the total information in y plus twice the total information in x plus some constant. This can be improved. We will have a look at the improved version of this a little bit later. Let's start by proving the first theorem. There is a constant c, that's what we want to prove. We are looking for a constant such that the descriptive complexity of a string x is less than or equal to the length of x plus c. So what we are saying is that there's always a way to describe a string x such that the length of the description does not exceed more than additive constant, more than an additive constant compared to the length of the string itself. This is very important. It would have been absurd if our descriptions of strings were actually longer than strings themselves. And what this theorem is saying is that's not the case. Our definition is actually quite sensible. If we use our method of describing strings, then we'll never have to pay too high of a penalty, even in the worst case. Let's look at a proof of this. So we start with this Turing machine M0, which is a very, very simple Turing machine. This Turing machine M0 does nothing. It, as soon as you start running it, just halts. So this Turing machine will not alter its tape at all. So whatever is the input to the Turing machine, that same thing is the output of this Turing machine. And this M0 is an extremely simple machine, and it's fixed. It's a fixed Turing machine, and therefore it has a fixed length description. Now what we can do is describe a string x by first describing this Turing machine M0 and following that with x. Let's see. So we can describe x by the description of M0 followed by x. Let's look at what is the size of this description. It is 2 times the length of the description of M0 plus the length of x. What is important here is that the length of M0 is independent of x. Hence, we can take c to be 2 times the length of M0 plus 2, and then we realize that this description of x has size the length of x plus this constant. And now, since d of x by definition is the shortest description, hence the shortest description cannot be longer than this particular description that we have described. And therefore, the length of the shortest description is less than or equal to the length of x plus this constant. So we have actually proved that k of x is always less than or equal to the length of x plus c. Let's review this proof a little more. Let's look at a little more detail of this proof. What we can do is we can follow a convention. We can say that M0 is described by the empty string. In that case, what is the description of x that I have shown in this proof? Well, if M0 is described by the empty string, the null string describes this null machine, then we can just leave out m. Why can't we just leave out m and write x? This is because anyone who's going to read our description is expecting to see description of some machine before they read the first 0, 1. Hence, if we agree that M0 will be denoted by the empty string, then we can simply send 0, 1 followed by x. But even in this case, as you see, the constant actually turns out to be 2. It's not 0. Why is that? Well, roughly, when we are sending the machine M0, we are trying to tell our friend on the other side that we have performed no encoding. There is no algorithm for you to follow. All you have to do is read what is being sent to you. But in that case, we will still have to inform the other party that there was no compression or there was no algorithm to be applied. That would at least require us to send 1 or 2 bits. In this case, it is accomplished by only 2 bits. Perhaps it can also be accomplished by one bit, but our goal is to come up with a theory not to save individual bits. We will leave that to the experts who do compression. What we will do is, what impact does this way of describing strings have on the definition of information, and what can we prove with it? Let's go on and prove our next little theorem. This theorem says that there is a constant C such that the descriptive complexity of x followed by x is less than or equal to the descriptive complexity of x plus a constant. So what this seems to be saying is that the string xx does not have much more information than the string x. Intuitively, how would you convince yourself that the string xx does not have much more information than the string x? Well, if I wanted to send xx to some friend, what I can do is I can send them x and then give them the instruction, well, double x. That would show that the descriptive complexity of xx is less than or equal to the length of x plus c. However, I want to show much more. X itself may be a very redundant string. Therefore, what I can do is I can send a description of x to my friend and then say, well, compute x from here and then double it. And that description is not much more than the description of x. Let's see the formal proof. We may be tempted to give the following proof. Let M1 be a Turing machine that doubles its string. That is, M1 is given by the following algorithm. On input x, output xx. We can now describe xx with M1 followed by x. However, this will only show that the descriptive complexity of xx is less than or equal to x plus c. So we have to be more clever. So now let's be more clever and let's formally prove that the descriptive complexity of xx is less than or equal to the descriptive complexity of x plus some universal constant. So the theorem we want to prove is there is a constant c such that the descriptive complexity of xx is less than or equal to the descriptive complexity of x plus c. Let M3 be a Turing machine that takes as input a Turing machine n followed by w as its input, and it doubles the output after running n on w. So our Turing machine m expects a Turing machine followed by a string, then it simulates the Turing machine that it gets on that string and produces some outputs, and it doubles that output. So the formal description of the Turing machine M is on input n followed by w, run n on w, and let s be the output of n on w. Now print ss on the output tape. The description of xx is now given by m followed by the description of x. Recall that d of x is the minimum length description of x. Clearly, if I give m the input d of x, then what it would do is it would first compute x and then double it. So it would eventually print xx on its output tape. So I can describe xx by this Turing machine M3 followed by d of x. This shows that the descriptive complexity of xx is equal to 2 times the length of M3 plus 2 plus the descriptive complexity of x. So I can take the universal constant to be the length of the description of M3 plus 2. And that proves our theorem. In the previous proof, d of x was the smallest description of x. We append the message, double your output, to obtain the description of xx. See, what we're doing is just sending the message double the output after computing x. And by simply sending this message double the output, appending it to the description of x actually produces xx. And since the instruction double the output is finite length and it does not depend on the string x, therefore it just adds an additive constant. We have to do it carefully in order for our friends to be able to unambiguously understand the statement, that is, that they will have to double the output after computing the description of x. Let's now prove something else. That there is a constant c such that the descriptive complexity of x, y is less than or equal to 2 times the descriptive complexity of x plus the descriptive complexity of y plus a constant. So what we want to say is that the amount of information in x followed by y cannot be a lot more than the amount of information in x plus the amount of information in y. Here we're saying something slightly weaker, which is that the amount of information in x, y cannot be much more than twice the amount of information in x plus the amount of information in y. This theorem can actually be improved, but let's start with this simpler theorem, which is easier to prove. Let M be a Turing machine that breaks its input string as follows. On input W, M finds the first 0, 1 in W. Then let's call the string that comes before 0, 1 as A, and the rest of the string B, the one that comes after 0, 1. M undoubles the string A into A prime. So what M does is every time it sees a 0, 0 in A, it puts a 0 in A prime. If it sees a 1, 1 in A, it puts a 1 in A prime. This is what we're saying undoubling of a string. Once M has computed A prime, it treats A prime as a description of some string and computes that string. So let S be the string that is described by A prime. So A prime is actually again going to be interpreted as a Turing machine followed by a string, and M is going to run that Turing machine onto that string, and whatever is the output, we are calling it S. T is going to be the string that is described by B. Now M simply outputs S followed by T. Now let's consider what M does on this string, which is double of the description of X followed by 0, 1 followed by the description of Y. Note that when M looks for a 0, 1, the thing on the right would be the double of description of X. When M undoubles that, it will get the description of X. So A prime is the description of X and B is going to be the description of Y. When M computes the string that is described by D of X, it will simply find X. Similarly, when M computes what is described by D of Y, it will find Y. Therefore, it will output X followed by Y. Let's now see what is the length of this description. Well, it's double the length of the description of X. Therefore, it's 2 times K of X plus there is a 0, 1 plus there is the length of the description of Y. So the length of this whole string is 2 times the length of description of X plus the length of description of Y plus a constant. Now we can describe the string XY by giving M followed by this string. Now running M on this string produces XY. Therefore, the descriptive complexity of XY is less than or equal to 2 times the descriptive complexity of X plus the descriptive complexity of Y plus the constant. Remember here that the constant I'm talking about is not 2, but it also has the length of the description of M in it. but we have been able to show what we wanted to prove. One can also show that there is an absolute constant C such that the descriptive complexity of x comma y is less than or equal to the descriptive complexity of x plus the descriptive complexity of y plus a constant plus 2 times log of the descriptive complexity of x. So one can actually reduce the constant 2 to a 1 at the cost of a logarithmic factor. This theorem is not very hard to prove, and I have asked you to prove this theorem in one of your exercises. Let's continue our discussion of descriptive complexity. Let's first see what we have already proved. We have in some sense said that the description of a string doesn't have to be much larger than the string. In fact, never is. Then we have said that if you look at the string which is repeated twice xx, that doesn't have much more information than the string x itself. Then in some sense we have said that the amount of information in x followed by y cannot be much more than the amount of information in x plus the amount of information in y. Now let us ask, how good is our definition? The way we have chosen to describe strings is by giving descriptions of Turing machines followed by strings. What if I were to use some other language? What if I were to use some other method of describing strings? For example, I could say that my algorithms are going to be written in a programming language like Java or C++ or some other language. What would happen to this whole theory if I were to replace those descriptions with Java descriptions? Instead of giving descriptions of Turing machines, I actually give descriptions of Java programs. Well, what we will show is that is not going to change the theory by very much. In fact, we'll show that our definition is extremely robust. Let's look at a practical example. For example, we let k Java x be the length of the shortest Java program that output x. The question is, what happens if we use k Java instead of k? Or what is the relationship between k Java and k? What we can show is k is within an additive constant of k Java. So, in some sense, the k that we have defined is universal. The notion of our descriptive complexity is universal. What we will do is we'll prove a much more general theorem that would not just talk about k Java, but it would talk about any computable procedure. Let P be a computable function which maps sigma star to sigma star. Here, sigma is 0, 1. We're always working with the alphabet 0, 1. For the rest of the discussion, we would always take sigma to be 0, 1. So we are looking at a function which is computable that takes some 0, 1 strings, and when you apply the function, it produces another 0, 1 string. We define the descriptive complexity with respect to P as follows. Suppose you want to describe a string x. Instead, what you can do is find a w such that P of w is equal to x. So the idea is, instead of sending x to your friend, you send them w, and they know that they can apply p to it and they'll get the answer. So d sub p of x is the shortest string w such that p of w equal to x. So d sub p of x is the shortest w such that I can apply p to this w and recover x. That is the descriptive complexity with respect to a computable function. So we are saying all we require is that this function should be computable. What is the relationship between the descriptive complexity with respect to a given computable function p and the way we have defined it? What we will do is we'll prove the following theorem, that given any computable function, there is a universal constant which depends on the function such that descriptive complexity of x is less than or equal to whatever is the descriptive complexity of x relative to p plus a constant c. The basic idea is that we can append an interpreter of Java in our description, and this changes the description length by a constant only. Let's be more formal about it. Remember that we have said that p is a computable function. Therefore, p can be computed by a Turing machine. Now let's consider the following Turing machine M. On input W, output P of W. Now let D sub P of x be the minimal description of x with respect to P. Then what we can do is we can take this one given Turing machine. M is one given Turing machine that only depends on P. We write down the description of M followed by dp of x. Well, if we send this string, this is a description of x. And therefore, we've been able to describe x in whatever is the length of dp of x, which we call kp of x, plus some universal constant. This shows that if you take any computable function, the definition of information that you would get, or the definition of how much amount of information you would get, would not differ too much from our definition. Let's now talk about another important and interesting concept. What we want to do is talk about incompressible strings. What is an incompressible string? Well, if you ask somebody who is in coding theory or somebody who is working in compression, they compress files and send them across and come up with nice methods of compressing strings, they would tell you an incompressible string is one that if you cannot compress. If you run compression algorithms on it, they do not reduce the size of the string. Roughly, that's our notion. We call a string be incompressible if you cannot compress it by more than b bits. So suppose a string has length x and its shortest description has length greater than or equal to n minus b. So we have a string x of length n, but its shortest description has length which is greater than n minus b, then we will say that the string is be incompressible. Suppose if a string cannot even be compressed by 1 bit, then we will say that that string is incompressible. What we want to do is prove a very nice and simple theorem which says that there are incompressible strings of every length. The proof of this theorem is going to be a simple counting argument. Let's start small. So let's think about why there are incompressible strings of length 1. Well, how many strings have length 1? How many 01 strings have length 1? I know of 2 of them. One of them is 0 and the other one is 1. Well, how many strings have length less than 1? Well, if a string has length less than 1, then it has length 0, and I know of only one string which has length 0, namely the empty string. So, if the description of 0 is going to be empty string, then the description of 1 cannot be the empty string and therefore will have length at least 1. On the other hand, if the description of 1 is the empty string, then 0 cannot have the same description as 1, and therefore the description of 0 is going to have at least length 1. Thus, out of these two strings 0 and 1, one of them must be incompressible. Let's go a bit further. How many strings we know which have length 2? There are 4, 0, 0, 0, 1, 1, 0, and 1, 1. And how many strings have length less than 2? Well, there are 3, namely the empty string, 0, and 1. So since there are 4 strings of length 2 and 3 strings of length less than 2, therefore one of these 4 strings must be incompressible. The argument is in general as follows. We start by counting how many strings of length n are there. There are exactly 2 to the n strings of length n. On the other hand, each description is also a string. So we count how many descriptions are there of length strictly less than n. Well, there are 2 to the 0 plus 2 to the 1 plus 2 to the 2 all the way up to 2 to the n minus 1 strings of length less than or equal to n minus 1. This is a simple geometric series. You must have understood how this geometric series is added, and this, if you add up this geometric series, you get 2 to the n minus 1, exactly 1 less than there are strings of length n. Therefore, there must be at least one string of length n whose description must exceed n minus 1, and that one string is incompressible. In the next lecture, we would look at a more general theorem which will talk about strings which are not decompressible, and then we'll look at some extremely interesting properties of these incompressible theorems. So incompressible strings look like random strings. We will prove it in an extremely general way. That would be the topic that we'll start with in the next lecture. I'll see you next time. Thank you and goodbye.